Okay, we'll get this little talk started for Robot Week here. I hope you're all having at least a informative and educational time this Robot Week 2024. First, I want to give a acknowledgments to the Ctest Rome and H2O groups for sponsoring this week's Robot Week and all of the festivities that we've had so far, and the snacks and treats that's have been given out. So I want to appreciate the folks at Ctest Labs for doing this. I also want to give a shout out to the Neo ACM. If any of you guys are out there that sponsored and helped us all during the year, and the ones that did make contributions to the robot designs and the software, and the good suggestions and advice that was out there, I want to give a shout out and acknowledgement to those folks, and to our RUR people out there. This one's for you. We stopped to kind of pause this year to make sure we kind of kept you guys updated too. So this small talk, we won't be long here. Just as more or less an update, a midweek update. Thank you all for listening and tuning in and participating this year in Robot Week. We have a couple things we want to, 2 or 3 items we want to cover and give everyone an update on. First is the ESI Clue Robotic Challenge that Ctest Labs is going to be sponsoring. The ESI Clue Robotic Challenge is a new challenge that Ctest is sponsoring, and that we're going to be launching sometime in 2024. I haven't got the exact schedule yet, but we do want to kind of do a knowledge drop here and let people know what was going on. The ESI Clue Robotics Challenge. Can your team of robots solve an environmental mystery? It's going to be a biennial robotics challenge, and it's sponsored by the Ctest Laboratories, the Rome lab there, Robot Microelectronics Lab, and the Northeast Ohio ACM. This is going to be an interesting one because they're trying a new format this time, and so we're going to try to speak a little bit about that, so you'll get some sense of what's going on. The environmental situation investigation. That's what this is about. This robot challenge is a challenge for a team of 3 to 5 autonomous robots that's going to have to solve some kind of environmental mystery using only basic physics, microscale chemistry, fundamental robotics, and logical inference. The ESI Clue Challenge is presented in the form of a game that the team of autonomous robots must collaboratively play. At the start of the game, an environmental mystery is discovered and announced, and it's going to be, the mystery will have occurred in some kind of curated environment, and a team of robots play the game by investigating the environment and identifying and isolating the cause of the mystery. So we have some effect. The robot's going to have to determine, I guess, or figure out the cause. And although the ESI Clue Challenge does include some routine tasks that robots perform, for example, monitoring and tracking, it's the 6 challenges that have not been met or not easily met by today's robots that makes the ESI Clue Challenge unique. And I might want to just put a note here. This is not a robot competition. For the most part, in a robot competition, robots those competitions tend to deal with solved problems. There's some set of rules, and everyone kind of knows what the solutions are to the problems, and it's a matter of, seeing who gets there first in the robot competitions, or who gets there in one piece, or whatever the competition is about. This is not a robot competition. This is a robot challenge. And for our purposes, a challenge includes one or more problems that have not been solved. And we're looking in the challenge to actually come up with solutions or partial solutions or near solutions to some of the problems. So keep that in mind, those of you out there that may get interested in this and might want to be interested in this. It will be open to anyone entering. You're going to see that this is going to be a challenge that will just be generally open. It's not even restricted to the United States. Folks in other countries can participate. But it's a challenge and not a competition. So hopefully that makes sense. And there are 6 challenges that make up the ESI, include robotics challenge, right? Keep in mind that this challenge is autonomous, meaning there's no remote controls, none, zip, nada, nilch, none. It's fully autonomous. And the challenges for these autonomous team of robots, first challenge is going to be object interaction in a 3D space. This challenge is going to involve sorting, transporting, and manipulation of objects that have been minimally specified. So your robots and the people who are involved in this challenge, they'll have some idea of the objects that will be manipulated, but they won't have total knowledge. So there's going to be some details left out about the objects, and the robots will have to be able to interact with those objects without complete information. Second challenge is going to be geometrical and analogical reasoning involved. I do know for a fact that the geometrical stuff will have to do largely with 2D angles and triangles and reasoning about those 2D angles and triangles. Old school analytic geometry, very old school. And then there's going to be some analogical reasoning by analogy about color. So this is unusual. I mean, these are different, and some of these stuff involve problems that are not solvable in polynomial time. So that's going to be a challenge. The third challenge is autonomous navigation. This challenge is going to involve navigating the curated environment. That's also going to be minimally specified. There will be some specifications and there will be some knowledge about the environment that will be passed out and known in advance. So it's not like the robots will be navigating a totally unknown environment. It will be known, but there will be incomplete information. And also the robots will have to navigate an ESI clue game board. So that's going to be interesting. I do know that a map of the game board will be available to all of the participants in that challenge. And so aspects of that's going to be known, and you will be able to figure some of that out. And then there's going to be, the fourth challenge is going to be robot-to-robot communication. The robots are going to be required to engage in two-way communication with the robot curator as well as with other teammates. So the robots are, in this case, will probably be heterogeneous robots. And they're going to have some kind of shared language in order to communicate about different aspects of the challenge. And so that's going to be unique. There's going to be a little bit of social epistemology with these robots. So that's going to be a challenge. It's easier said than done, let me say that. Then there's robot to human communication challenge, where the robots are going to be required to explain and justify the solution to the mystery. So if your team of robots were lucky enough or fortunate enough or smart enough to figure out the cause of the mystery, the underlining thing that caused the anomaly, they will have to communicate that cause and justify that solution in terms that a human can understand. So That's somewhat challenging. There are a number of ways to do that. We'll talk more about that in the future. And then the last is there's going to be time-constrained inference and computation. These challenges have a finite window. And within that finite window, the robots are going to have to perform some logical inference and computation over some somewhat large search spaces. So it is not going to be the case that the robots will be able to take their time exploring and figuring out the mystery. They're going to have to do so under the clock. And some of this stuff is it's not been solved. Some of this kind of inference, and so these 6 challenges are really the things that make the ESI Clue Robotics Challenge a challenge, and not a competition. And as we noted earlier on, that challenge is a biennial challenge. So it's once every other year that the actual challenge will take place. Okay, and so here's how it's going to work. The ESI challenge is broken down into 6 qualifiers. The qualifiers are scheduled at 4-month intervals leading up to the ESI Clue game. Participants can compete in the challenge remotely. That's one of the unique things this time. And spectators can watch the challenge over Zoom, YouTube Live, or similar internet connections. So this is going to be the kind of thing that whereas last time we were looking for our robot challenge, all the participants to be there in person and all the robots to be in person, many aspects of this challenge are going to be able to be performed remotely, and participants will be able to do big portions of it in their own robot labs. Okay, and now any team that has achieved a satisfactory score in all 6 challenges, they may participate in the ESI Clue Challenge semifinal game. Okay, this game will also support remote participation, and each robot team will be able to play the game remotely and be viewable over Zoom, YouTube Live, or some similar internet connection. The details for how that's all going to work out, we're going to make that available in due course, so you guys are going to see how all that works. But the fun thing and the important thing that we want to get out in Robot Week this year is that we have a new format for a robot competition and a new way to do it remotely so that more people can participate, and so we don't have all of the travel involved, and tearing down the robots and rebuilding the robots and the environments and everything. That can just cause undue and unnecessary wear and tear on the robots and the environment. So we're going to try to let as much as possible be done in place, and then at the last, for the very final competition, we're going to have some things happen in person. Okay, and so we'll have a version of it, a semifinal ESI Clue challenge will be done remotely for those teams that have managed to get enough scores a high enough score in all 6 challenges. They can play the semifinal game, and then the top scores out of that challenge, the top 3 scores that were able to complete all of the remote challenges, they will be able to compete live in the ESI Clue Grand Final Challenge that's sponsored by Ctest Labs and the Neo ACM. So that should be interesting news this year for Robot Week. So we look like we're having a good Robot Week so far, and this is going to give everybody a lot to work for over 2024, the rest of 2024, and throughout 2025. Now, so that's enough about that. We also want to drop a brief note on the robot programming software that we've been our teams have been working with over for 2023 and 2022, and this software, ROSE, we call it. And it's for ROSE stands for Robot Scenario and Situation Editor. This is a nice piece of software that lets us model and describe the environment to the robot. So traditionally, the robot actions are programmed, and there's a focus on agent loops, and there's a focus on sensor behavior and motor behavior and those kind of things. But there's not very much attention spent programming or modeling the environment. This software allows the roboticist to actually provide a model of the robot, model of the world to the robot. And it's not super sophisticated, but it's better than nothing. And so it's called ROSE. And those of you that are participating and involved in RUR and involved in our current robot challenges, those of you that don't have the software, get in contact with me, and I will make that available, show you how to get it. And so it has 6 primary components to it. We can directly program the robot. We can give the robot some task to program. And let me just contrast those two things. In direct programming, you're telling the robot to do something very specific. Maybe move so many meters, or you want the robot arm to move in 3D space to some specific location. You want the gripper or the end effector to do something specific, and you are telling the robot explicitly what to do. You're not using a remote control, but you are giving the robot a direct command. Perform some specific action with the actuators or the sensors or the effectors or the manipulator, right? In task programming, we give the robot something, a higher level, and some kind of goal to perform, and the robot determines on its own which actions it needs to perform in order to accomplish that goal. So this is more in the agent-oriented programming kind of paradigm. And then the thing on the top row here, stories programming. That's where we actually we give the robot a context, a story, a situation, and a scenario, and the robot is asked to resolve that scenario or story or situation. And that's even a higher level type of programming than task. So at the top row, the lowest level things is direct, and level above that is called task programming. And then the highest level is we just give the robot a story or a situation or scenario, and it has to resolve that. We're also able to teach the robot about itself with the robot profile. So these robots will not only, as we use our software, the robots not only have a model of the world, they have a model of themselves. So they know what they are capable of. They have like meta knowledge of their own actuators, manipulators, end effectors. They know about their processors. They know about their, how much battery life they have, how much, what the voltage requirements are of their parts. It's a self-knowledge. And so that's what that robot profile is all about. And then the scenario reports is something that it's a way that the robot can asynchronously report back to the programmer its success or failure in performing one of the things on the top row here. So as far as direct programming or task programming or storage programming, the scenario report is an asynchronous thing, meaning that the robot can be given a task on a Monday and perform that task Monday or Tuesday or Wednesday, and on Thursday the programmer can come and look at the report and have some sense of what the robot did, how it succeeded or failed or whatever. And then there's a unit test module that has all of the unit tests as self-checks for the robot. So that's an interesting thing here. And this is, I just threw a screenshot of this out just so that those people who haven't seen the software have some idea what they're looking at. This is just a shot from the task programming screen. And so when I say a task, we might ask the robot to locate something. We might ask the robot to retrieve something, but we don't specify details. Like in the direct programming mode, details are specified. In this task programming mode, we give a high-level goal, and the robot figures out what actions it needs to use. So, determine is asking the robot to compute or infer or, identify something. It's a lot that goes into that. And so we have travel input. So there's 5 very high-level type of tasks that we ask the robot to perform. And you go in here. If you kind of drill down to here, here's an example of locate. We might ask the robot to locate something, some kind of object. Maybe we give the object's ID and won't say where it is. Maybe we're not specifying the object. Maybe we want the robot to locate the nearest object or the furthest object away from its sensors. Or maybe we want the robot to locate any object that it can locate. Or maybe the first object that it can get to, as opposed to the nearest object that maybe it can't get to. There's some tricky stuff here. We have the ability to specify some attributes for those objects. It's an interesting thing. And then we put a time limit on that request. And this dialogue here kind of lets us know what we can do. We're not running it, so you can't really see what this gets translated into. These commands, what you would find out when you, for those of you that haven't used it yet, all these dialog boxes are all translated into some kind of logic program, either Prolog or answer set or something along those lines. So you fill in a dialogue, and that immediately gets translated into a logic programming language. And in fact, all of the subsystems on the robot that we have been working with for the last year, 2 years, all those subsystems communicate using a common logic interchange format. Here's another example. Maybe we are asking a robot to travel to some particular Cartesian coordinate. We have units as always, whether it's a GPS location, polar coordinates, we have a time limit, we have a maximum or minimum speed. And for this dialogue, this is a situation where we're asking the robot to travel to some location, but we're not saying how to get there. We're not saying whether you're going to use Dijkstra's shortest path algorithm or, you're going to use some other kind of a brute force method. We're not specifying anything to do with obstacle avoidance. That's going to be up to the robot to determine. So while it seems like we're providing a lot of information here to the robot, we're not. This is a pretty scant information in terms of telling the robot to go to some location. And not giving it too much beyond that. And so this is an example of what these dialogues look like. We're going to get a chance. We're going to I think we're going to have a more pronounced presentation in 2 or 3 weeks. I think we're going to be doing a talk for the ACM, Neo-ACM this year for their July General Assembly meeting. And I think we're going to present some more of this software and some of how it behaves and how you actually interact with the robot. Not sure about that. I think there's a big probability though. So for those of you that want to see how some of this works sooner rather than later, the Neo-ACM General Assembly in either July or August will be your first opportunity to see that. Right? And then this is a little bit from the situation scenario report where the robot is going to give you some details about objects or things in the environment that it interacted with. It's going to give you any actions that it attempted, what the status of those actions were, which objects were involved in the action, if there was measurements required. what those measurements were, what the values were, units. It's a lot of information. If the robot had to make any assertions, so this is part of the situation report screen, and this is an asynchronous thing. The robot generates and does the work, and then it generates this report, and it sends this report, to the user machine, wherever that is in the world. So it doesn't. This something works on these robots work on their own intranet, and so if you have a station that's connected to the intranet, not internet, intranet, robot intranet, you can get a situation report from your robot or your team of robots, right? So it's an interesting thing. And so real quickly here, that was kind of like a quick update on the ROSE software, and just letting you guys know where we're at on that. And lastly here, some of you had problems with using the Raspberry Pi to communicate over serial and Bluetooth simultaneously, right? And so I wanted to share a little bit of our solution on that. We have a similar thing here. Our robots that we're working on right now, they have a number of subsystems. They have a Raspberry Pi. Right now, I think all of the controllers are 3B pluses, maybe 4s. They have a Raspberry Pi, and that Raspberry Pi is kind of like the primary controller for 4 or more Arduino controllers, right? So we definitely have a situation where we want to send Bluetooth, use Bluetooth communication from Raspberry Pi to one of the Arduinos, and maybe use a serial port, just a straight line connection to another one of another one of the Arduinos. And so we've run into that situation where we've been tempted to do that simultaneously, and you run into all kinds of problems. The serial port is identified as dev TTYS0 on at least on the Raspberry Pis we have, and the Bluetooth channel is actually also associated with that same port. So, and there are ways around it, but those ways tended to be too problematic and unpredictable and unreliable. And so we really asked ourselves, is it really the case that we really need to use both of those ports simultaneously? As we went back and analyzed our tasks, what we're asking the robot to do, we needed it to be used concurrently, but not necessarily simultaneously. So when we say concurrent, we mean kind of over the same time period. And so what we were able to do was use them in a serial fashion, but it happened so fast till, from the layman or the observer point of view, it looks like it's simultaneous, but it's not. It just, if we need something to happen over a 5-second time period, it was fine for us to use one of those connections first, close it, and then open the other connection and use that. And we're able to do that within our time constraint. And so for those of you out there that are having trouble trying to get the Raspberry Pis to talk to, if you have Raspberry Pi, let's say 4 and or less, trying to get those serial ports and the Bluetooth communication to happen at the exact same time. Maybe you don't need them to. I would suggest trying to see if you can do the access in a serial fashion, meaning you do one thing first and wait till that thing is done and do the next thing after that. You'd be surprised how fast that happens. Like I said, we've been able to get very, very short intervals where we use the serial port first and then Bluetooth, or Bluetooth first and then serial. And in between using them, we close the port under one protocol and opened it again under the other protocol. So like in this situation, I had our Raspberry Pi controller has to talk to the Prism Arduino subsystem. And the Raspberry Pi controller has to talk to this Robotics Phantom ARM subsystem. Initially, we thought we needed to do that at exactly the same instant, and it is not the case. As long as we do it with, within the same interval of time, that's appropriate, right? And if you have something that's more stringent than that, maybe you might want to consider adding another piece of hardware than going through all of the trouble with reprogramming the Raspberry Pi operating system to let you use those the primary and the minor serial ports simultaneously. So that's just a note for those of you that are trying to get that done. We had to, in this situation, like I said, we want to use the Raspberry Pi to talk to this Prism and to talk to that. That's a veneer, the red shield there. That's a veneer shield. We have sensors, analog and digital sensors on our robots use those shields. And so we might talk to the shield with Bluetooth or serial. We might talk to the Prism with Bluetooth or serial or vice versa. Okay? And so the issue is you can't talk to both of those devices at the exact same time. But we were able to successfully talk to them in a serial fashion, and over a very short interval, which gives the illusion of a simultaneous connection. So, our recommendation for those of you that are struggling with that is to give that a try. Now, if someone has figured out how to safely and successfully and reliably use both of those protocols at the exact same time over that single piece of hardware, get in touch with us and let us know. We'd be interested to find out that solution and to share it with others so that we can share it with other folks that are running into the same thing. Okay? We threw out a little code to let you know what we did. We checked to see if the requirement on a part was Bluetooth. And if it wasn't, if it is, we construct a Bluetooth device, and if it's not, we construct a normal TTY device. We set up the device that gets picked at that time, and we set up the communication protocols, and then you send the request, right? You get the receipt back. You receive back any kind of response, and ultimately, what you do is you close the connection at that point, and you delete that object, right? And so at that point, the channel and all of the structures and buffers have been freed and let loose. And then when you come back into this loop again, you create whatever device you need. So this thing is running in a loop, what you're looking at on the screen here. And each time through that loop, it creates the device, creates the storage, creates the sets the protocol, it sends the message, it gets the response back, decodes that, and then closes the device and deletes it. And so basically freeing up all of the buffers and those things. This has worked for us for the last 6 or 7 months or so. It's been pretty good. And so we can say, at least in our case, that this is a reliable solution. And we realize that we don't have the detail for some of these methods up there. Those of you that need to know those details that haven't already gotten them from us, get in contact with me, and I have no problem sending them to you. Like for instance, the setup communication method, we set the device and we do an open and we do a connect, right? And then here's like what one of those connects look like. So if we're doing a Bluetooth, we we connect to a Bluetooth socket here, right? Most of you guys know how all of this works. And if there's some kind of problem, we throw an exception. So again, most of you should have this code already. The ones that don't and are still struggling with this, contact me at Ctest Labs, and I'll be happy to share it with you. And that's all I got to say for today. So, I want everybody to, thanks for, like I say, tuning in. And I want everybody to enjoy the rest of Robot Week. And hopefully we will see all of you in ESI Clue Robotics Challenge. See you guys soon.